Yesterday we set ourselves the problem that if you measure in some scattering process a differential cross-section, how do you determine what the amplitudes are in a particular case of spinless particle scattering? So here is an example of a differential cross-section at a given energy for some spinless process, and it has structure in it. And these structures tell you something about the spins of the amplitudes that are contributing. And in general, the more wiggles they have, the higher the spin. That's essentially the basic idea. And we saw yesterday that these wiggles correspond essentially to zeros of the amplitude, the zeros of the amplitude at real values of the energy, but at complex values of cos theta. So, and the real part of the position of the zero is where it appears, as you see, and the height is related to the imaginary part of the amplitude, the imaginary part of the position of the zero. So, by plotting zeros or seeing the dips in the cross-section, you already know something about the structure of the amplitude, and it's directly related to physical quantities. So what we saw yesterday was, I'm going to call my amplitude like I did yesterday, F, but we're going to change a little bit later the notation, but nevertheless we will be able to do that. We saw that this could be written from the differential cross-section, so this is the normalization, namely the amplitude. Well, let me write the modulus of the amplitude in the forward direction, and then a product of terms of the zeros of the, and this factor here is on the bottom is just to normalize these, and the zi's are the positions, the complex values of the zeros. And this then is directly related to the cross-section, and there are two things I want you to note. First of all, the modulus squared of this is related to the differential cross-section in the forward direction, and sorry, I should have put the forward direction there and the backward direction there. So it's normalized to the cross-section there. But of course we don't know what the phase is. So there is always, in here, you can insert some phase, e to the I phi, which of course is not determined because the differential cross-section is the modulus squared of the amplitude. Now, these zeros are, as I said, at complex positions, and in this little picture here, at least in the physical region, because there are 1, 2, 3, you don't quite know how many zeros there might be, but there are at least 3, maybe more, that in writing down the amplitude, you don't know whether to put here the position, the zero, or its complex conjugate. So you can replace, construct a new amplitude by doing that for each of the zeros. And so that means if there are n zeros, there are 2 to the n amplitudes. Now, 2 to the n different amplitudes, and this is called the Barillet ambiguity. Now, this is named after a Frenchman who now does astrophysics, but in fact, this is a very useful technique because though it's very easily seen here in spinless particle scattering, it equally applies when there are spins involved. And so it is a generalization of this. Now, 2 to the n minus 1 amplitudes are different, and the others are the complex conjugates of them. So there are actually 2 to the n minus 1 amplitudes which describe exactly the same experimental data times 2, which are just the complex conjugates of the others. So this means that you can have a large number of amplitudes that describe exactly the same experimental data. Now, just to give you an illustration of how different the amplitudes can be, if you have some structure with the dominant here, let's imagine there are 3 or 4 wiggles, 4 zeros, let's say, then the leading partial wave amplitudes, well, maybe I have to remind you that you can write this as a sum over the partial wave amplitudes. So these are the partial wave amplitudes which are complex at a given energy, written in terms of the eigenfunctions of angular momentum, which are the Legendre polynomials. And that's just a different way of writing this same expression, because clearly the Legendre polynomials are polynomials. So let us write this in a sort of notation which is common, a spectroscopic notation, which is, so to emphasize, these are functions of energy. So there is an S wave component which corresponds to L equals 0, and then there is a P wave component which corresponds to L equals 1, and a D wave component which and so on. So you just write out each of the Legendre polynomials like that. So imagine that the spin 2 component was the dominant one. Imagine that you had 2 dips in this. Then what you would find in going from one amplitude to another, that if you look at the vector, let's say for the D wave, so this is the old-fashioned atomic spectroscopy notation. So let's say the S wave was like that, and let's make the P wave like that. So imagine those are the vectors given by one of these amplitudes. Now what happens when you make a change and replace 1, 0 by its complex conjugate? What happens is that the leading one, the biggest one, stays more or less where it is, but the others change. So another amplitude will be, it doesn't have to be in exactly the same direction, but like that. And then you find that S goes this way and P goes like that, or something like that. So they completely change the structure of the amplitudes. And the question is, how do you know which of these many ones is the right one? And to do that, you need more information to be able to do that. And this is provided by other constraints of S-matrix theory, in particular unitarity, and that's the property that we're going to go to. So if you had many, many amplitudes, you can do this. The other drawback, and something related to what Marco Battiglieri talked about yesterday, is that, let me do something else first. It's very useful to recognize that these, at least the ones inside the physical region, namely these dips, are physical quantities, namely they correspond to dips in the cross-section. So if you go to the Mandelstam plane, which is essentially where all of the action takes place, and you consider the S channel, and we forget about assume the process, all the masses are the same, so this is the S channel physical region, then you find where the zeros are. They're at real values of S, but complex values of cos theta, which means complex values of t, and we plot the real part. And what you find is that these dips move along lines. They move along lines like this, something like this, for example. So you, from one energy to another energy, they are continuous. Okay, so zeros of the amplitude don't just happen, they move continuously with energy. And they're continuous. Two aspects of the continuity are important. One, this is the real part, so this is the real part of Z, or Z, that I've plotted, but the relationship between one barrel amplitude and another is to change the imaginary part of the position of the zero. So imaginary part, imagine that this is the place where you do your experiment, and the imaginary part is sort of outside this, it's on top of this, it's moved out a little bit, okay? And so each of these zeros has an imaginary part, which corresponds to the height of these. Now these are also continuous. So what I've shown here is that you have this ambiguity at every energy, but it doesn't jump from one energy to another. So imagine we plot 1, 0, doesn't matter which one it is, Zi, as a function of S, or the square root of S. So here as a function of root S. And we do this at one particular energy, and this particular zero has an imaginary part which is either here or here. Okay, one is just the complex conjugate of the other. And that's supposed to indicate that there is an error bar associated with the experiment. Now, at the next energy, you will also have two solutions, let's say. Maybe goes another energy, it does this, and so on. Now, the amplitude is continuous. And so, if your amplitude is equal to for whatever reason, the correct one is this one, then at the next energy, it's not here. Okay, it's that one. Okay, so continuity tells you how they are connected to each other. And the only place, so if for some reason you knew that these were the continuous, this was the right solution, the one in the top half, because it satisfied unitarity and the other one didn't, for example. Then the only place where they can change is if the solutions essentially do this. It will become maybe the error bars are supposed to be. So the lower ones are just the complex conjugates of the other. So only where the imaginary part becomes very small, then you see that if you knew it was the top one, if you knew this was the right solution here, it could either be this track or it could be this track. So it's only where the imaginary part becomes small for any of the zeros that you can swap from one solution to another solution. So this means, though you appear to have a large number of amplitudes, it's not that number at every possible energy. They are connected to each other. Now, the other important aspect of these is that they connect dynamics. So let's see how they connect dynamics. Let me maybe erase this. If you have a resonance with a particular spin, then some particular partial wave amplitude, one of these, will be big. And because that will be big, let us imagine it's the P wave, the spin 1, then we know that the amplitude will be dominated by this term, and so there will be a 0 in the angular distribution at cos theta equals 0. And as I mentioned yesterday, if you have spin 1 entirely dominated, then the cross-section would actually look like this. Okay. So, what do these zeros actually do? We know that where the spin 1 resonance appears. So imagine here is the energy, this is S plotted this way, and we're in the S channel. Let us imagine that along these lines, at this energy we have a spin 1 resonance, here we have a spin 2 resonance, and here we have a spin 3 resonance. Then we know that the spin 1 resonance, if it dominated and there was nothing else, there would have to be a 0 at this point, which corresponds to this dip here. And if there is a spin 2 resonance at some other energy, it's got to have 2 dips. And if there is a spin 3 resonance, then there have to be 3 dips. Okay. Now, I already mentioned that the zeros of an amplitude, it's a complex function, don't just suddenly appear. They are connected from one energy to another. So these zeros here are called Legendre zeros because they correspond to the zeros of the Legendre polynomial. And they're connected from one energy to another. You perhaps can already see how they might be connected. Namely, this 0, which ensures this guy is a spin 1 resonance, because it has 1 0, is one of the zeros that makes it this one a spin 2, and this one a spin 3. So these zeros are often connected to each other along lines like that. And they go from one energy region to another. And similarly, these are connected to each other. Okay, so physically, they are connected to each other, and in the low energy region, where there are only a small number of partial waves, the amplitude starts out flat and then has more and more structure. And what happens is that zeros essentially come into the physical region from outside, either through the forward direction or the backward direction, and sometimes both, depending on the process. And so the backward and forward amplitudes go up and down as a zero comes in, and these where they line themselves up to be the zeros of the Legendre polynomials is exactly where the resonances of that spin appear. Now these zeros are continuous, and they connect not only one resonance to another, but they also connect low energy to high energy. So if we have meson-meson scattering, and one example would be pi-pi to pi-pi, or equally pi-k to pi-k, or whatever, pseudoscalar mesons, these pseudoscalar mesons are related to the property of chiral symmetry breaking. And chiral symmetry breaking requires that in the low energy region, in the region of the Mandelstam triangle, which is an unphysical region, not in either of the three channels, there the amplitude is small. In fact, it has a zero. And so one of these zeros actually passes through the Mandelstam triangle and goes out the other side. And it provides a connection between something called an Adler zero, which is low energy, with what is happening at other energies. It becomes the Legendre zero of resonances. And then in the high energy region, it becomes where the process is dominated by something called Regge exchanges, which if we get time, we get to. The Regge amplitudes, which are dominated by high energy behavior, also have zeros, and these become the zeros of the Regge amplitudes. So they connect from one energy to another. And that's one of the beauties of the zeros, is that they are continuous, and you can see them by just looking at the data, how they go from one energy region to another. So they connect dynamics, and they connect chiral dynamics, so what is happening in the low energy near threshold region. They connect those to resonances, and then they connect them to Regge. So in fact, spectroscopy, you may know, we haven't actually discussed this yet, but the resonances correspond to poles of the amplitude. What you see is that the pole of an amplitude tells you have a resonance, but the zeros in the amplitude tell you something about that resonance, namely what its spin is. And these are connected. The interplay of zeros and poles is what hadron dynamics is about. So zeros and poles imply, or they make up, hadron dynamics. And probably I have done something very bad, namely I have written on this board, and that's not recorded. But okay, you can at least see it. Now, before we will come back to this a little bit later, but I want to just show you how, which is what we're going to go to, how unitarity can limit the amplitudes. But I want to mention something related back to Marco's seminar yesterday, which is that clearly from the experimental data, you can only see a finite number of wiggles. So by definition, n is a finite number, 2 or 3. And so this means that the partial waves stop at some point. The ... is actually 0. And it turns out that that is something that it shouldn't be. There should be very small components of higher waves, and normally they are not important if you want to find some dominant resonance or some dominant partial wave. But if you're trying to determine for example, some gluonic excitation with unusual quantum numbers, which may be only a few % of the cross-section and hence be on this plot some very small vector, then this will be disturbed by the fact that you truncate it. And so the higher partial waves have an effect on the lower ones. And so, as Marco was emphasizing, if you want to study the main details of a scattering process, that we know, and we know what the dominant resonances are and how they fit into the quark model, and I'll remind you of some of that in a second. But the small effects are controlled by the need, by an approximation. They're affected by an approximation. And so you have to find some way to remove that harsh truncation. So the partial wave amplitudes, the amplitudes as a function of L. So here are the amplitudes, whatever their size is. For each L there is a line, one of these, the length of one of these vectors. And we assume that after some point they're equal to 0. Whereas in fact, there are very little pieces that are here, which in fact we can know something about. And these little bits have an effect on some of these, not the big one. Let's say this is the big one. That's not going to be affected by the little amounts of the other partial waves. But the little amount of the other partial waves affect, so this is the modulus of the partial wave amplitudes. The fact that we put these equal to 0 can have an effect on these ones, and particularly if you want to know them precisely. Now, for the dominant partial waves, we know their structure very well, and so we can plot. I mentioned yesterday, if you consider the states with the highest angular momentum, then if we plot here the total spin as a function of mass squared, we have here at some scale spin 1. We have on here the rho, the omega, the k star. So these lines, I've put lines rather than dots just so that you can see them better. The rho, omega and phi have, I shouldn't have put them like that, sorry, I didn't do this quite right. So let me do it better. Spin 1, we've got the rho and omega, and then we have here the k star, and here we have the phi. And we know that they belong to some quark model multiplet, which has, in the quark system has spin 1 and no units of orbital angular momentum in the quark model. And then we can find, again, the next spin 2. So the spin 2 guys form a similar quark model multiplet at higher masses, and so we have here the A2 and the F2 and the K2 star, and probably you can't see my tiny writing, and the F2 primed. And they belong again to a simple quark model multiplet, where now instead of S equals 1, L equals 0, which were these guys, these are, maybe I should have written here, this is S equals 1, L equals 0 in the quark model. This is S equals 1, L equals 1. So to have a unit of orbital angular momentum in the quark model costs energy, and so you get a set of higher states, and these have essentially the same structure. And you can do the same again for spin 3, and so on. So there are the states that sit here with S equals 1 again, L equals 2, and so on. And in fact, we know quite a number of these. Now those with the highest spin that we observe, they're the easiest ones to observe, because they're the ones, because they have the highest spin, produce the most wiggles in the angular distribution, and they're most easy to determine. These all have, in the quark model, the two quarks have in a spin 1 system, and then you have added units of orbital angular momentum to make their total spin. Those are the ones, they are called the ones that lie along the leading Regge trajectory. Doesn't matter if you don't know what that word means at the moment. Hopefully we will get to that. But there are many other states which have lower masses, the same mass, but lower angular momentum. So states, for example, in the same mass region as these, but have spin 0, and those here that have spin 1, and here, again, those that have spin 0. So all of these lower ones are more complicated, and they are not exactly like those given in the quark model, because their decays play a much more important role. They get shifted, they get moved, and we'll maybe come back to that. So though the leading states fit very nicely in the quark model, the lower states, which you expect, for example, with s equals 1 and s equals 0 and L equals, with s equals 1 and L equals 1, you can't just make spin 2, you can also make spin 1 and spin 0, total spins. And so these states should also exist in the quark model, but they don't have quite this simple structure of ideally mixed quark model multiplets in which the heaviest state is always made out of a strange and an anti-strange quark. Okay. If we get time, we'll come to that. So what I want to come to next is a little bit of S-matrix formalism, which I don't want to spend too much time on, and in fact Pete used some of what we need, but we need some definitions just to be able to at least motivate what comes next as far as unitarity is concerned. So we're going to take maybe 10 minutes on what you might call S-matrix formalism, and I'm assuming that this is the kind of thing that you can look up in a textbook if it's not familiar to you, or I just give you a reminder. So, what is the S-matrix? The S-matrix is a giant matrix which takes you from all possible initial states to all possible final states, in which all the initial states have every possible momentum and the final state has every possible momentum, and the only thing that connects them is the quantum numbers have to be right, match each other, and momentum has to be conserved. And that's what this giant matrix does. And the giant matrix has this property that it says the probability that something happens, namely initial state goes to a final state, the probability is 1. Okay, that's what essentially the key property is that it has. Now, to define this, we need something that Pete mentioned, which is something called Lorentz invariant phase space. And Pete gave a formula for this. So for a state of momentum capital P, so for the Lorentz invariant phase space for a single particle of momentum P, it's equal to d4p over 2 pi cubed, and a delta function which says that the particle is on its mass shell, so its 4 momentum squared is m squared. And then, because this delta function enables you to do one of the integrals, namely it enables you under an integral to do the time component, you can equally well write this as d3p divided by 2 pi cubed, and it brings down a factor of 2 times the energy. So these are equivalent to each other under an integral. And the only other bit of formalism we need, so this is for one particle. So if there are n particles, the Lorentz invariant phase space of the particles from Q1 of momentum up to Qn is equal to 1 over 2 pi cubed n, and a product of each of these terms, d3qi over 2ei. So that's just a formal bit of how you count the number of particles in a box or whatever, which tells you something about how you normalize amplitudes. And in fact, for a single particle, this normalization tells you that the integral over Lorentz invariant phase space of a particle between one momentum and another, this is equal to 1. Essentially, it's just saying the wave function of that particle is 1, the probability of finding it in a box. Now, the S matrix, as I said, is a giant matrix that takes you from the initial state to all final states. And what can happen is, of course, that the particles don't interact at all. So the particles just go past each other, and that's not interesting at all. So we separate that part out, and we write the S matrix element going from some initial state to some final state as being a term which has got the initial state to the final state and nothing happening at all, plus a piece which depends on the transition, namely an interaction has taken place. So this is the sum over the initial momenta minus the sum over final momenta, and I apologize, I use I sometimes as an index, and here it's used as initial and final. And then this is I times T, and this is called the transition matrix, or the T matrix. So the piece that we're interested in, the amplitudes that we calculate, are these transition matrix elements where we want something to have happened. And the definition of a cross-section, and this you just have to believe me, for AB to go to N, the cross-section from initial state AB to go to N particles is equal to some factor which is 1 over 4p times the square root of S, and p is the center of mass momentum, free momentum of the AB system. And then we have the integral d Lorentz invariant phase space for the particles Q1, all the final state particles up to Qn. And then we have a delta function which just ensures that momentum is conserved, which says that PA, the initial momenta, PA plus PB, is equal to the sum of all the momenta of the final state particles times the modulus squared of a final state with momentum Q1 up to Qn, and technically speaking these have got to be in states which we're not going to worry about, and PA, PB of the again in states. So it's the modulus squared. So the formal definition of a cross-section is that it's equal to some integral over Lorentz invariant phase space. It says that the initial and final momenta have to be conserved, and it's the modulus squared of this matrix element, which takes us from particles AB to this set of N particles. And that's all we need. And this normalization, well, why it's that, you have to read about why that is. Now, the S matrix is unitary, and this gives us a very important property which we can make use of. So let me erase this, then I can keep the formula that was there before. So let's, instead of writing lots of delta functions and what have you, let's note that the S matrix has the property that this must be true. So it says S dagger S, its complex conjugate transformed, times the S matrix is equal to the unit matrix. And you can write this as S times S dagger, whichever way you like. And so we're going to write S symbolically plus IT, where this is what IT is. And then when you substitute that into there, you can see that that tells you 1 minus IT dagger, I plus IT, is equal to the identity. And then you just rearrange this, and this tells you that I T minus T dagger plus T dagger T is equal to 0. And now forgetting that this is a matrix, t minus t dagger, a function time minus its complex conjugate, is 2i times its imaginary part. So this tells you that 2 times the imaginary part of t, and there's a minus sign, so we can put this term onto the other side. So it says that 2 times the imaginary part of a particular matrix element from some initial state to a final state is equal to t dagger t, the matrix element from the initial state to the same final state. So that's a particular, since this is a matrix equation, this is true for each element. And t dagger t means just multiply 2 matrices by each other. So this is equal, and when you multiply 2 matrices, you sum. So this is t star fn times tn I. Now, a particularly useful case that tells you something rather important is what happens if the initial state and the final state are the same. So we have AB goes to AB, the same particles, and since the label I and F label all of their momenta, all of their properties, there's a very particular case when the initial momenta and the final momenta are the same. Namely, the particles have scattered, but they go off with exactly the same momentum in exactly the same direction as they started with. So if I equals F, which corresponds to what's called elastic scattering, because the particles scatter elastically, the same initially, and I equals F means that the scattering angle is equal to 0, namely they go off in exactly the same angle that they did before, then this tells us something here. So let's see if we can, I don't want to erase too many things here. So it tells us that 2 times the imaginary part of T elastic at S and theta equals 0 is equal to this sum. And this sum means the sum over n, and remember that when we multiply these we have to include the Lorentz invariant phase space for each of the particles, so it's the sum of the particles from the initial state to some general final state, so Q1 up to Qn, a delta function, probably there's a 2 pi to the 4, which I haven't written, a factor of 2 pi to the 4, delta function of PA plus PB minus sum Qi, and then if the initial state is equal to the final state, then maybe I should have written one more line here. 2 times the imaginary part of Tii is equal to a sum over n, the modulus of Tni squared. So I've just put I equal to initial state equal to the final state, and then what that means is Q1, Q2, up to Qn, T, Pa, Pb, modulus squared. So, the unitarity relation says that 2 times the imaginary part of the elastic amplitude is equal to that quantity there. But as you see from what is on the board, this equation, each of these is equal to the cross-section for AB to go to n. So all of this factor, we can go from here, using the equation that's on the board, is equal to the sum over n, 4p the square root of s, the cross-section for AB to go to n. And probably I should have taken the kinematic factor outside of that sum. And then, obviously, the sum over n of AB to go to n is what we call the total cross-section. It's the cross-section for AB to go to anything. So this is equal to 4p root s times sigma total, which means the sum of AB to anything. That's what it means. Okay. So unitarity says there is a theorem which is usually called the optical theorem, which says that the total cross-section for the process AB goes to absolutely everything is equal to, just taking into account the factors of 2, 1 over 2p the square root of s times the imaginary part of the elastic amplitude. So that's called the optical theorem. It says that the total cross-section for a process, AB to go to anything, is related to the imaginary part of the amplitude for AB to go to AB, the forward part of it. Now, I'm sure you've met that before. Now, we probably want to do another step, and then we can have a short break. So let me go another maybe 15 minutes. This we can relate to the amplitude for the process. Let's consider the cross-section, which I defined yesterday. The cross-section for, let's say, AB go to AB. That's equal to, well, there's some momentum factors, but they, because the initial and final momenta are the same, it's 64 pi squared times the modulus of the amplitude. And I'm going to call the amplitude t just to match what t is here. So let me again put a label just for once so that you know that it's the elastic amplitude. S and z, which is cos theta squared. So the differential cross-section for AB goes to AB we had yesterday is equal to this. Now, we know that the total cross-section is the cross-section for AB to go to anything. One part of it is the cross-section for AB to go to AB, and then there are many, many other channels. So let's turn this also into a cross-section. This is a differential cross-section. This is a total cross-section. So what we need to do is integrate this over omega. So what we're going to define is the cross-section which is called the elastic cross-section. AB goes to AB, so that's what elastic means here, which is equal to 1 over 64 pi squared s, the integral over omega, which means over the azimuthal angle, the integral over cos theta, which goes from -1 to +1, or the angle theta goes from 0 to pi, and the modulus of this amplitude. Now, to be able to do the integral and compare what is here with here, it's useful to do something that we introduced yesterday, which is to expand the amplitude, to separate out the amplitude into what are called partial wave amplitudes. Why do we do that? Partial wave amplitudes are things that have definite angular momentum, and we do that because it enables us to separate this amplitude here into pieces that depend on the energy and pieces that depend on cos theta. So we define, and then we'll come back and put it in there. Maybe I do it over here. We define that t of s and z is equal to, and just for convenience, we'll put in a 16 pi. I didn't do that yesterday because I wanted to make life simple. And so to differentiate the guy with the 16 pi, I'm going to call this TL. So these are the same Legendre polynomials we had before, and these are the partial wave amplitudes. And what we're going to do is substitute this equation into here, and when we do that, then we can obviously do the integral over cos theta over z. So let's do that. Well, first of all, we can do the integral over phi, because if it's spinless particle scattering, nothing depends on phi, so we get a factor of 2 pi. So there's a factor of 32 pi s that sits in front. And then we've got the integral from -1 to 1 dz to do. And we've got to write this, that partial wave expansion, for the amplitude and its complex conjugate. So each one has got a 16 pi, so let me put that in front, 16 pi squared. And then the amplitude, or its complex conjugate, whichever way round you like. So here is the complex conjugate, PL. And then the sum of the terms for the amplitude itself. So all I've done is write down the partial wave expansion for the amplitude and its complex conjugate. And then the other property we need is that the integral of the Legendre polynomials is equal to 0 unless L and L primed are equal, and then there is a normalization of 2L plus 1. So we can pull all the z integral through this and just keep this PL and PL primed, and there's a factor of a half, which we'll take care of. So it should be 16 pi, if I've done this right, 16 pi over s, the sum over L, 2L plus 1. One of the 2L plus 1s cancels with the normalization there, and L primed have to be equal. So this is equal to this, and these are functions of s. So it's equal to that. So the elastic cross-section is equal to a sum essentially over the modulus squared of the partial wave amplitudes. And the optical theorem tells you that the total cross-section, which contains more than the elastic amplitudes, is equal to this factor, where it's the same amplitude, but involves only the imaginary part. So let's write down what sigma total is. Sigma total is equal to, for exactly the same process, is equal to, and we're going to substitute again a 16 pi. So we get 16 pi over 2p root s, that's that tp root s, and then the sum L equals 0 to infinity, 2L plus 1, the imaginary part of the TL of s, which are the imaginary parts of these, times the Legendre polynomials at cos theta equals 1, namely in the forward direction. But the Legendre polynomials have the property that in the forward direction they're all equal to 1. So we see that if we collect these formulae together, that clearly sigma total has to be greater or than equal to sigma elastic, because the total cross-section for AB to go to anything has obviously got to be bigger than the cross-section for AB goes to AB, tells us that the sum 2L plus 1 of the imaginary parts of the partial wave amplitudes is equal to 2p over root s times the sum L 2L plus 1, the modulus of TL of s squared. So it should be greater than or equal. Okay. Now, one very important thing that I perhaps should immediately tell you that follows from here is that though amplitudes are complex, so they can have not only real and imaginary parts, but the real and imaginary parts in principle can be positive or negative. But what we see is that the imaginary part of the forward amplitude is related to a total cross-section, and total cross-sections are obviously positive, so that tells you the imaginary parts are in fact positive, and in fact it means actually that every one of these imaginary parts of every partial wave in fact is positive. Now, if I had taken another half an hour, which I'm not going to, we could then show that actually this equation holds not just for the sum, but it actually holds for each partial wave separately. A thought experiment you can imagine is, since this is purely mathematics at this point, think of the scattering process happening through one particular L. L equals 27 or whatever your favorite number is, and all the other ones would be 0. Then it would obviously be true that you only needed to put L equals 27 on the two sides of the equation. And you do that essentially for every partial wave. To prove it formally, you have to do a little bit more work than I've just done. Now, to get to a suitable point just to stop, where we can start again and then we can see what the consequences of this are, is you can show, that the imaginary part of the elastic, is greater than or equal to 2p over root s, the modulus of TL of s. Now that obviously tells you the imaginary part has to be positive because it's bigger than a number that's obviously positive. And in the case, now these are the amplitudes, these are the partial wave amplitudes for something that's called elastic. Namely, the initial state and the final state are the same. Very confusingly, elastic is also used in another sense. We said the total cross-section is obviously greater than or equal to the elastic cross-section. But in the low energy region, AB going to anything, the only process it can go to is AB goes to AB. So then the total cross-section and the elastic cross-section are equal, and we would have an equality. That's also called the elastic region. When you pass some new threshold, so the simplest example would be, let's say, pi-pi scattering. At low energies, pi-pi can only go to pi-pi. As the energy increases, pi-pi can go to 4-pi, 6-pi, and so on. So there is a low energy region in which kinematically only pi-pi can go to pi-pi, and that's called the elastic region. Not to be confused with elastic scattering. They are related, but not exactly the same. So, in the region below what is called the inelastic threshold, this is an equality. Okay. And that equality is called elastic unitarity. Okay, so that's a good place to have to ask a question or have a break. Okay, so if we stop for whatever, 8 minutes, is that all right? Okay. There are two things that we need to do yet. One is something relatively simple, which is to understand how to represent this relationship, what it's actually telling us. And one of the things that's interesting about it is that it's non-linear. Namely, it's a feature of strong interaction amplitudes. That, you see, it says the imaginary part of an amplitude, when it's an equality, is related to the modulus squared. So this tells you you can't multiply the amplitudes by 2 and they still satisfy the equation. It normalizes them, it fixes them. So it does something different that can happen with Feynman diagrams, in which the relationships are always linear, and we'll see that. So let's do two things that will be familiar to you. So though I've done this for spinless particle scattering, it applies for the equivalent for any process, pi n to pi n or whatever. And let's first look in the region below the inelastic threshold. So for pi n scattering, that would be before you can create another pion, pi n. Then this is an equality. That's the first thing we're going to do. The second thing, so you know where we're going, is that you see there is this factor here. This is a threshold factor which says P is the center of mass momentum. So it says the imaginary part is related to the 3 momentum. So below the threshold, there is no imaginary part. And above the threshold, there is an imaginary part. And that tells you something about the analytic structure of these functions. And we'll come to that. But let's do the simple bit first. So when it's an equality, we've got, obviously, you don't need to write this, is equal to, it's convenient to call this something. So I'm going to call it rho. People who work in chiral perturbation theory, which is a sort of modern thing as far as people of my age group are concerned, call this quantity sigma. But for me, that's very confusing because sigma is a cross-section. And then you get funny equations in which sigma equals sigma times something, and that looks very strange. So historically, it was called rho. And so this equation says, in the elastic region, for each partial wave amplitude, that is true. Okay. Now, what you see is it tells you something about the modulus of the amplitude. As you can easily see, let's write TL is the modulus times a phase. And the phase is usually written as delta, and it depends on L. And then when you substitute that into that equation, you see that the left-hand side is sine delta L, and the other side is rho times the modulus of TL squared. And so that tells you that TL, the modulus, is equal to 1 over rho times sine delta L. And I'm sure you've met before that elastic unitarity says that the phase and the modulus of the amplitudes are related. Now, importantly, as I said, it's a nonlinear equation. So, it tells you, if you know the phase, you know the modulus, and if you know the modulus, you know the phase. That's only in this elastic region. Something perhaps I should draw your attention to is that when the momentum goes to 0 at the threshold, rho goes to 0. Well then, so you've got a 1 over 0 here, and you might worry about that, but you can show that delta L, these phase shifts, go like a constant times the momentum to the 2L plus 1. So they have more than enough powers to take care of this, so the answer is finite. Now that's what happens in the region of elastic unitarity. Now, it's perhaps useful to write this in another way, which is that we can write this sine delta L as e to the I delta L minus e to the minus I delta L over 2I times e to the I delta L. So all I've done is write sine delta L in a way which I hope you recognize. And then this is equal to 1 over 2I rho e to the 2I delta L minus. Okay. So that's what the representation of the amplitude is in the region of elastic unitarity. But above the inelastic threshold, then there is clearly, this just says the total cross-section is equal to the elastic cross-section, and now above the inelastic threshold we have to add another piece, essentially the inelastic cross-sections. So for energies, or square root of s, above the inelastic threshold, in other words, when you can produce other particles than the ones you started with, then the relation says, it's just convenient to write it like this, is equal to rho times the modulus of TL squared. And then you have to add a piece. So it's traditional to add it like this, where this is related to the inelastic cross-section. So this is related to the inelastic cross-section. And then the solution of that equation looks like this one, but it obviously is only equal to that one when e to L is equal to 1. So in fact then TL is equal to 1 over 2I rho e to L times e to the 2I delta L minus 1. So the partial wave amplitude has the same form, but now e to L is not equal to 1. This is called the elasticity. So when eta is equal to 1, it's elastic. And this is called the phase shift. Now, it's convenient, and I'm sure you must have seen this before, to plot a complex function in what is called the Argand plane. So we can plot something which we call little tl, which is rho times capital TL. And this is the axis of im TL. And this is the axis of real TL. And this is a unit circle, so this height is a half. So that points I over 2. And then this amplitude here, in general, is a vector like that. So that would be the vector TL, would be inside this circle, where if I draw that line, this has length eta over 2, and that angle is 2 delta. And that is just a representation of exactly this formula. because it starts from from the circle. From a circle whose center is I over 2, so that's why it's like that. Now when eta is equal to 1, namely it's elastic, then this vector is on the circle. So elastic unitarity, namely this equation, says that the amplitude is on the circle. Okay. So when eta equals 1, the amplitude is a vector. TL is on the circle. Okay. And then, if you remember some geometry that you did at school, the tangent, that angle is also delta. That the angle delta and the angle 2 delta are the same. I mean, they're related to each other. The angle at the center is twice the angle, like that. So when eta equals 1, it's on the circle, and when it's inelastic, it's inside the circle. And what you see is that the imaginary part is always positive, because this is the origin here. So partial wave amplitudes of elastic processes, and it's only elastic processes that's true, because the optical theorem is related to the imaginary part of the elastic amplitude. So if you have some amplitude pi n to sigma lambda or whatever is sigma k or whatever is allowed, that is a process in which imaginary parts can be negative as well as positive, because it's not related to a cross-section anymore. Now, all of you will have learnt perturbation theory. And perturbation theory satisfies unitarity perturbatively. For the electroweak interaction, that's perfectly fine, because the coupling is small, so the square of the coupling or the cube of the coupling is also small. But for the strong interaction, the coupling is big, and so satisfying unitarity is an important property. So imagine you have a Feynman diagram for some process, which is like this, some particle being exchanged. So this is the lowest order amplitude, where these are the couplings G. Then your partial wave amplitude, or your amplitude. The partial wave amplitude will be order G squared. So that will be the lowest order. And then you'll have a set of higher order Feynman diagrams. Now unitarity says that the imaginary part of T is related to the modulus of T squared. So it immediately tells you that the imaginary part of the amplitude, for a Feynman amplitude, the lowest order was order G squared, this must be order G to the 4. So imaginary parts in unitarity, in Feynman diagrams, only happen at the next order, by taking the square of these diagrams. So for example, so that's essentially the modulus squared of that amplitude. You have to have a loop, and this loop has an imaginary part, and that's of order G to the 4. Now when you study perturbation theory, you make sure that the right and left-hand sides are satisfied, but they're only satisfied order by order. The crucial thing about the unitarity relation that we've plotted here is that it's exactly satisfied. Okay. And clearly when amplitude, so that's fine if your vectors that you're considering are very, very tiny. Probably you can't see them. So imagine the vector is very, very tiny like this. Then it doesn't matter. Satisfying unitarity is perturbative. But as soon as the strong interaction becomes strong and the amplitudes are significant, then one order of perturbation theory of order g to the 4 can be as big as the amplitudes of order g squared. So here we had an example in which the real and imaginary parts are roughly the same size. And so perturbation theory breaks down. So that's one of the important things about the strong interaction, is that unitarity has to be satisfied rather precisely, otherwise you can't satisfy the dynamics, and that's because it's a strong interaction process. So the next thing we need is, what are the consequences of this factor rho? So let's see, it tells us something about the structure of amplitudes. And so I'm going to go off T. So let's start with this equation. Where rho is equal to this factor. And to make life simple, we're going to think of a simpler function. And see, what it tells you is, physically, is that their contribution, this is elastic unitarity. As you part, well, maybe I'll make the comment later. Maybe it'll be easier to understand when I go later. So let's perhaps first do the mathematics. What we're going to do, first of all, let's imagine that we have all masses equal, just to make life simple. And then we remember that P will be equal to 1 half S minus 4m squared. And so we don't have to write 4m squared, which is the threshold. We'll call it S sub t. So this is the square root of S minus st. So let's see what having such a factor means for an amplitude. So we first do a little bit of mathematics. So what we're going to look at, imagine here is the complex S-plane. And this is the point S equals st. Is this point. I'll label it a little bit later. And then we're going to evaluate a function at 4 different places. We're going to evaluate it here, 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 and here. And we'll call the function A, at that point A, this one B, this one C, and this D, and that's the point S equals st. And because this is a slightly complicated function, we're going to consider a simpler function. Consider a function g of s, which is equal to the square root of st minus s. Why we do that, it'll become clear. And we're going to evaluate that function at these 4 different points. And we're going to do it because it has a square root. We always have a choice as to whether we should take the positive square root or the negative square root. So we're going to make the choice now to make the positive square root. And we'll worry about what happens when we take the negative. So choose the positive square root. So now let's first look at the point A. And we need to know what S is at that point. So there's the point A. And we're going to call the length of that line alpha squared, and that angle phi. So SA is equal to ST plus alpha squared e to the I phi. I hope everybody's happy that that's true. And at B, SB is equal to ST plus alpha squared. Let's imagine it's the same distance. That's the same distance. That's also alpha squared. E to the I pi minus phi. And C is at ST plus alpha squared e to the I pi plus phi. So phi is some angle, and we're going right the way round to opposite it. And then we go to D, which is going to be ST plus alpha squared e to the I 2 pi minus phi. Now we're going to evaluate the function g at each of those points and see what happens. Once you've done one, it's easy to do that. So at A, st minus sa is what we have to evaluate, and then we have to take the square root. So that's going to be equal to minus alpha squared e to the I phi. And because we're going to take the square root of minus 1, we need to decide what is the square root of minus 1. And we're going to choose the positive square root. So we're going to write this as e to the I pi alpha squared e to the I phi. And we'll worry about if it's the other one afterwards. So now we can write down what g is at this point. G is the square root of this. I hope I've left myself enough space. It's alpha e to the I pi plus phi over 2, which is I times alpha e to the I phi over 2. Is that okay? Now let's do the same at B. St minus Sb is equal to minus alpha squared e to the I pi minus phi, which is equal to the e to the I pi alpha squared e to the I pi minus phi. And g at Sb, since there's a minus I e to the I pi and e to the, so that's e to the 2 I pi, so we can take the square root of that, which is minus 1, alpha e to the minus I phi over 2. And if you are not sure at any step, please say. Now we've got two more to do. St minus Sc equals minus alpha squared e to the I pi plus phi, which if I short circuit two lines is e to the 2 pi plus phi alpha squared. So the square root of that is minus alpha e to the I phi over 2. And then the last one equals minus alpha squared e to the I 2 pi plus minus phi. The minus sign gives us another factor of pi, so that's 3 pi minus phi times alpha squared, and then we have to square root it. And e to the I 3 pi over 2 is minus I alpha e to the minus I phi over 2. Now, so it's just a case of keeping track of the pi's, the phases. Okay, and every time when there was a minus 1, I've called it e to the I pi. That corresponds to taking the positive square root. We're going to also see what happens if you take the minus sign afterwards. Now, this angle we called phi. That angle is also phi. That angle is also phi, all of those. So let's do the easy one first. What happens if I make B and C come close to each other, which means letting phi go to 0? What you see is that the difference between these goes to 0. If you let phi get smaller and smaller, they become small. Okay. So maybe I can write that over here. So whichever way round G at SB minus G at SC, let's just write down what the answer is. It's minus alpha e to the minus I phi over 2 minus e to the I phi over 2. And that's equal to 2i, so that's minus 2i alpha sine phi over 2, if I've done that right. And what you see is it goes to 0 when phi goes to 0. So that tells us that this function is continuous when you cross that line, and that shouldn't be a surprise because it's st minus s, and if you're at a point where s is below st, nothing happens. But now let's take the difference between what happens at A and D. G of SA minus G of SD is equal to I alpha e to the I phi over 2 from the top one, and the bottom one is minus, so this is plus I alpha e to the minus I phi over 2, which is equal to 2I alpha cos phi over 2. And now we see when we let phi go to 0, the answer isn't the same. This goes to 2I alpha, so this goes to 2I alpha when phi goes to 0. So this square root function, when s is bigger than st, has a different value here than a value here. There's a discontinuity between those values, and so the function is said to have a cut. It has a cut along the axis starting at st. So the function, usually drawn like here, has a cut. So this point and this point, those two amplitudes are not the same. Those two functions are not the same. Okay, I can probably erase this bit. Our partial wave amplitudes, in fact the whole amplitude, will have such a cut. Now we can learn something else. Oh, I erased the two, but I shouldn't have done. This was A and this was D. I probably have to write it again. SA equals ST plus alpha squared e to the I phi and SD equals ST. Well, it doesn't actually, we didn't need that. I didn't need actually to write it again, so let me. Let us notice that at the point B and C, when phi goes to 0, it's the same function. So there's no cut here below the threshold. There's no problem. But here there is. Now, there is a relationship between the value of the function at this point and the value of the function at that point. G at the point SD, well, the first thing to notice about SD is that it's just the complex conjugate of A. So this is the same as SA, but the complex conjugate, because complex conjugate in a complex plane means just cross the imaginary axis. Now look at the answer that we got. The value of the function at the point SD is minus I alpha e to the minus I phi over 2. You see that that is just the complex conjugate of what this value is. So we see that this is the complex conjugate of the value at A. So the function in general doesn't just depend on any point. G at the complex conjugate point is the complex conjugate of the function. And such a function is called real analytic. So the function in the top half plane is the complex conjugate of the function in the lower half plane. Now, we need to do just two other things. When we've taken the positive square root, we're said to be on sheet 1. And then the function, if I try to so this is the real s-axis. So this is an attempt to draw it in 3 dimensions. So the function had a cut starting at s there. It has a discontinuity. The value at that point and the value at that point are not the same. There's a discontinuity. So that was the function on where we took the positive square root. Now, let me see if I can use another color. Maybe I have to write here. So here are our 2 points, SA and SD. And on sheet 1, just to copy down, we've got G of SA equals I alpha e to the I phi over 2. And again on sheet 1, G of SD is equal to minus I alpha e to the minus I phi over 2. Now let's imagine that we took the negative square root. What would that mean? That would mean everything on this side, everywhere I had a minus 1, instead of writing e to the I pi, I'd write e to the minus I pi. So I can do that on the board. I can put a minus sign there. I can put a minus sign there. And I get a minus sign there. That's not a surprise because we've taken the opposite square root, so there should be a minus sign. It's not going to change these guys, so we don't need to worry about them. And if we take the minus square root again, this will be e to the minus I pi. So this will now, this factor will become e to the I pi, and this will go to the opposite sign with a plus sign. So the changes are the ones in yellow. So what you notice, of course, is that the value at the 2 points went and changed sign. Not surprisingly, we took the square root with the opposite sign. So there is another sheet which we can draw in exactly the same way, sheet number 2. It also has a discontinuity, but on sheet 2, G of SA equals minus I alpha e to the I phi over 2. And on sheet 2, G of SD is equal to plus I alpha e to the minus I phi over 2. So on each sheet, the function has a discontinuity. The value at A and D are not the same. But do you notice something? On sheet 1, at SA, it's equal to I alpha e to the I phi over 2. And on sheet 2, at SD, it's I alpha e to the minus I phi over 2. So if I let phi go to 0, this becomes I alpha, and this one becomes I alpha. So the sheets are connected to each other. So probably when I get to use the projector, I will be able to show you a better picture than I can possibly draw. But the two sheets are connected. So here's the cut. This is sheet 1. And here's sheet 2. Now there's a cut along here which says you can't go from here to here. But we've just seen that the amplitude there on the top here and the one on the bottom are connected. So you can go from this point to this point on the bottom one, even though you can't go to this point. You have to go round the cut to get to it. But this point is connected to that point, and this one is connected to that point. So those two are connected, these two are connected, but those across the cut aren't connected. Now where you do your experiments is on the top sheet. That's just a definition. You choose which sheet is the one. So experiments are done, probably I need a colour. Experiments are done along here. But the poles which correspond to resonances are on the unphysical sheet, and they're on this sheet. So resonance poles, why that is, we'll come to. The nearest unphysical sheet. Now we did this with a particular example which wasn't quite the function, but it has the same analytic properties. So let me go on a few more minutes. So when you have the imaginary part of TL, This function is slightly more complicated, but the factor on the bottom doesn't make any difference. If you don't believe me, well, maybe you can work it out for yourself. The actual function we want to consider is not quite g, but is that ratio. But it has the same analytic properties. That's what elastic unitarity says. It says that at the first threshold, the amplitude has a cut. Now, unitarity says that every time you pass a threshold, there are new imaginary parts. So this was the contribution from the elastic channel, but we know there are other pieces that you have to add when you cross the inelastic thresholds, and they correspond to new cuts, new parts to the imaginary part. So there's another discontinuity, which starts at the next threshold, and so on. So let's label them, I don't know, whatever. Imagine your favorite process is pi n to pi n. So this would be pi n threshold, and the next one would be 2 pi n threshold, and maybe this is 3 pi n threshold, and then some other particles, whatever. And there will be contributions to the imaginary part at every threshold, and they will add. And while here there are 2 sheets, here there are 4 sheets, then there become 8 sheets. And then you can imagine in general, with the S matrix, there are millions of sheets. And the poles that correspond to the resonance particles are always on the nearest sheet. Some are nearer than others. Maybe that's a complication we don't need to worry about just now. Maybe that's a good place to stop. I don't know whether I should start on anything else. Maybe people have questions. So scattering amplitudes are analytic functions. They have this property of real analyticity, which tells you that the function here and the function there are the complex conjugates of each other. The amplitudes have discontinuities. The discontinuities happen, well, maybe I should tell you one more thing. Here is the Mandelstam plane where all of the action is taking place. And this is the S-channel physical region, somewhere in here, T-channel here, U-channel here. At every threshold that you pass, at each threshold, we have new contributions to the discontinuity that build up the contributions to the imaginary part of the amplitudes. The same thing, of course, is happening in the T-channel and the U-channel. So at every threshold in each of these channels, they may be completely different channels. You know, in this channel it might be proton-antiproton goes to pi-pi, whereas in that channel it would be pion-proton goes to pi-proton. So they're completely different processes with different thresholds. What do these thresholds do to our amplitudes? Well, they generate new discontinuities of our amplitude, but as you see, these discontinuities happen with S negative. It corresponds to the physical region of the T channel and the U channel. So this function that we have, which has what's called a right-hand cut, which comes from the thresholds in the S channel, also has cuts on this side, which will start at different places, which correspond to satisfying unitarity in the T channel and the U channel. So these are called left-hand cuts for obvious reason. And these come from the cross channel. And these are called right-hand cuts. And they come from the direct channel, the channel you're in. So scattering amplitudes have a complicated analytic structure, determined by unitarity. And you can make use of that property to tell you about something about the amplitudes. They satisfy relationships, have to satisfy relationships. Okay, is that a good place to stop? Yeah? Too much to start on something else. So, please ask questions if you need to.